I'm Satyajit Bose. I'm a lecturer in discipline at Columbia University's School of Continuing Education and the Earth Institute. What you're about to see is a set of 3 lectures on the mathematical essentials necessary to go through our Master of Science in Sustainability Management program. This is the 3rd of 3 sessions. Since it took us a little longer last time, we will spend the first hour discussing multivariate calculus, which we didn't get to, and then we'll talk about summation and integration, and then the last hour we'll talk about probability. I will not do statistics today. I know I had promised that to you, and I'm sure you're terribly disappointed. But most of the statistics that you will need is covered in the primer that I distributed over the summer. And what I will do before we get, if you're taking my economics class, before we get to the topic where you really need to know the statistics, I'll have an extra recitation session after one of those classes to give you a primer on statistics. So that'll probably be 8 p.m. to 10 p.m. some Monday night. Okay. So multivariate calculus, we're going to do multivariate functions and talk about partial differentiation, which you'll see is an analog of ordinary differentiation. So let's just jump into that. Remember that when we were talking about univariate functions, then we said that we would look for the derivative, we would look for a point on the function where the derivative of that function was equal to 0. Alternatively, the point on the function where the tangent line to that function at that point is horizontal. And if we had a convex function, then such a point would be a local minimum. And if we have a concave function, such a point would be a local maximum. Everybody recall this? Everybody remember that this is the concave function? Okay. Okay, so what are multivariate functions? So far, we've had f of x as a function of one variable x. Now, suppose we have a multivariate function, some function that depends on 2 variables. You would think that most functions are probably like that. Most real-world functions depend on a number of variables. For example, you might think of agricultural yield as a function of labor input as well as fertilizer input, and maybe soil quality and irrigation or rainfall and so on. So in principle, it could be many different x variables. Okay? In this case, the x1 and x2 variables are b and z. And so we have yield as a function of labor, b, and z, fertilizer input. For a variable of 2 functions, you can display it on a 3-dimensional graph, just like for a function, sorry, I think I switched that around, right? For a function of 2 variables, you can display the graph of that function on a 3-dimensional Cartesian surface, just like for a 1-variable function, we displayed the graph on a 2-dimensional Cartesian plane. Okay? This is yield as a function of labor input and fertilizer. So I've got fertilizer on this axis and labor on that axis, with yield going up vertically. Okay, you can't really read the labor there too well. So if you think about this surface, it looks like a hill that starts out at 0, where labor input is 0 and fertilizer input is 0, so yield is 0. The units of yield would be in terms of bushels of corn and so on.
Per acre or something?
Bushels of corn per acre, yes, since we haven't included land in this. Okay. And then as you increase labor, while keeping, if you were to increase labor while keeping fertilizer 0, in essence, you would have very little output. But if you were to increase labor and fertilizer, so if you were to move out this way, then you can see yield is going to rise sharply till it'll reach some maximum, beyond which adding more fertilizer and labor, that is going out this way, will actually reduce yield. Okay? So clearly, so one use of this function might be simply to ask, for a certain number of units of fertilizer and labor, what's the yield, right? And you would simply plug that in. So let's say if you wanted 2 units of labor and 3 units of fertilizer, you'd plug in 2 for B and 3 for Z and work out what Y would be. And that's what we've done here. And you can satisfy yourself later that the answer would be 30. Okay? An interesting question might be, suppose that you fix one of the inputs only, how would the yield vary as you varied the other input? So you hold constant one input, and you ask, how would yield vary as you vary the other input? Okay? And in this case, we say, let's suppose we hold constant labor units at 2. Okay? So we're not going to, we're only going to put in 2 units of labor. So the labor is along this axis. So you look for the value of 2 along that axis. Let's say that that's over here. Holding labor constant at 2 means that you're looking for a cross-section of this surface that goes along this line, okay, with B equal to 2. And if you're looking for a cross-section, it's going to look, you will be able to display it on a 2-dimensional surface. Where we have fertilizer on one axis, yield on the other, okay? And in fact, the way we're going to write this is yield given, this line here indicates given or conditional on, labor input equal to 2, okay? And I would take a cross section of that hill, and it would look something like this. Okay? Everybody clear? Okay. So this function tells me how yield would vary as fertilizer input varies, holding constant labor input. And if you wanted to know what was the functional form of this equation here, of this function here, you would simply plug in the value 2 into that equation, which is what we've done here, and you'll get 18 plus 10z minus 2z squared. Okay, so let's do an example. You may come across this example in one of your classes on energy efficiency or sustainable building design. suppose you have a building with very simple dimensions, a length, a width, and a height. Okay, so we have a rectangular building. Given the dimensions of that building, so length x, width, y, and height, it should be z, right? It doesn't. I think I cropped something when I pulled that picture in. So that's z. I have here a table which tells me the rate of heat loss for each of the sides of the building as a function of the dimension. So this is the heat loss per square foot. Obviously, the roof has the highest heat loss, as does the north side. So this is obviously a building in the northern hemisphere. If you were in Australia, you'd switch them around. Well, you switch that and that around. And this is the area of each of those sides. So the total heat loss is given by this function. Okay, so 10 times xy is the heat loss from the roof, plus 8 times yz is the heat loss from the east side, and so on. Okay, everybody with me? When you simplify this expression out, you'll get this, which is a function of xy, yz, and xz. And you can ask, well, for particular values of x, y, and z, what is the rate of heat loss? And so if x were equal to 100 and y was equal to 70 and z were equal to 50, what's the heat loss rate? And this would be in therms. It might be 201,000 therms per hour, let's say. Okay? So that's simple enough. We're going to talk in a moment about trying to minimize that objective function, minimize heat loss. Before we jump to that, let's talk about level curves. Okay, level curves you've all met before, I'm sure. Anybody know of a level curve that they are used to seeing? Okay, so you probably have not heard the term level curve before, but a level curve is a locus or a set of points which have the same characteristic, either on a Cartesian plane or on some other projection. And one of the level curves that I'm sure you've met are contours, altitude contours, right? So if you look on a map, you'll find lines which connect different points on a geography which are of the same height, the same altitude, right? Those are level curves. You've probably all seen weather maps with lines that connect different points that have the same temperature, or points that have the same average precipitation, or points that have the same pressure. Okay, those are all level curves. Now, mathematically, you could think of a level curve for a three-dimensional function, for a three-dimensional graph, meaning a function of 2 dimensions, as all the combinations of x1 and x2, that is, all the combinations of the input variables, which give you the same output. Okay, so let's go back to our fertilizer and labor to yield function. This is a hill. If you were to draw a map of this hill looking down from above, what would it look like? So you're looking down from above. Okay, you're looking down from above, so you're going to see fertilizer on one axis and labor on the other axis, right? Concentric circles centered on the maximum of the function, right? Okay, so that's exactly the same as the contour maps that you would see, and you could write the equation of one of those contour lines in the following way. Y as a function of bz is equal to some particular constant. Okay, that is, if I were to look for all values of b and z such that the yield is equal to, let's say, 30, which is that value there, so I'd be lopping it off right there. Then I'd find a set of combinations of b and z such that yield is 40. Okay, so I could solve the equation for this level curve, but just by setting this value equal to 30, and then I have a then I've defined my locus. Now, does anyone remember implicit differentiation from last time? Yes, that cross section. Is that also considered a level curve? No, this is not a level curve. That's the level curve that is holding the output constant. This is simply, this is usually referred to as a cross section. Yeah. Okay. Okay, we'll talk about implicit differentiation in a second. So for a fixed number c, the graph of this equation, f as a function of x, y equal to c, is called the level curve of height c. Okay, that's exactly what we did up here. Okay. For example, isotherms, which we just talked about, this line connects every combination of x and y. So in this projection, combinations of x and y translate into what? What are x and y in this conceptual projection? Latitude, coordinates, right? Latitude and longitude. If I go this way, I'm changing longitude. And if I go that way, I'm changing latitude. And these are just combinations of longitude and latitude which have the same temperature at a particular point in time. So you would think of, if I were to draw a three-dimensional representation of this map, it would look like a, I'd have the map of the US laid out horizontally on the ground with a hill starting down here and rising up to this top here, the hottest point in the US. Okay? Everybody see that? Okay. So how do I get, here's another place, here's another function. Here I've got f as a function of x and y. You should get used to using different letters for the different input and output variables. So you notice, for example, that I've used f as a function of x1 and x2, y as a function of b and z. Now I've got f as a function of x and y. So suddenly here y is an input variable, not an output variable. Okay, so you need to look at the context of the problem to determine what's an input variable and what's an output variable. This is, the function is x squared plus y squared. When you draw level curves of this function, they'll just be concentric circles around the origin. Okay, a very common type of level curve that you'll see in economic analysis are isoquants. Okay, iso, recall in Greek, means equal, hence isotherms are points of equal temperature. Isoquants are loci of combinations of inputs, in this case labor and capital, combinations of inputs, labor and capital, that yield the same quantity of output. Okay? So this is the function, and that's the height of that function. So here 60L to the 3/4 times k to the quarter is a production function. Okay, it gives you the output in units of output for the level of labor and capital that enters the production process. This is a very common function used in economic analysis. Now, suppose that I'm looking for the level curve of this function at height 600. Well, how do I do that? I set that function equal to 600. Then I pick which input variable I want on the x-axis. And which one I want on the y-axis. The one I want on the y-axis is the one that I solve for. Okay. Say I want, well actually I guess I did it the other way around. Say I want capital on the y-axis and labor on the x-axis. So I'm drawing, this is, I'm looking down on the production function from above. This is a map of all combinations of labor and capital such that output is equal to 600. So I have to solve this equation, my production function set equal to 600. I solve that for k. So I'm just dividing both sides by 60L to the 3/4, and then taking it to the 4th power, which is why it's 10 to the 4th power and this to the 4th power. So I get a level curve that looks like this, and the equation for this curve is 10,000 over L cubed. Okay, so there will be times when you know the production function of some technological process, and you have to solve for the level curve at a particular quantity of output, or you may not know the technological process, and you may simply observe these econometric relationships in the data, and you may be trying to estimate the production function. Okay? And so they will be related in this way. And here is the graph I just drew.